Good morning, Howard. Good morning, Sean and Cheng Rui. Yun Tong, you're the first today, so you get extra point for YouTube participation. Hi, Amelia. Good morning. Jia Hong, good morning. Oh, you guys are all early. I guess you are probably still awake, maybe 2 a.m. This early morning, and yet coming to the lecture this morning. Hi, Catfish. And hi, Xuehan. 幼鱼雨节. All right. Okay. So let's start with the announcement. First thing is, of course, hi, Xinghui. Hui Xing, I'm sorry about that. So the lecture link, the Google Meet calling link, and I saw actually some of you started working on PA3 and some of you might have completed it. So there's a special announcement about PA3 you might want to look into before you start. So if you just go to PA3 channel, if you have already added PA3 channel into your channel list, then clicking here should take you to PA3 channel. Okay, you see that there are a few announcements here. Take a look of these in order to make sure that you do not struggle too much about PA3. Try to use pa3-test.txt as input, which you should all have it in your team account's home directory. So Polly is actually god of the server, so she just planted this into your account. All right. Use this as the input file for PA3. See if you can upload this this file to the server that Polly has already set up running. Okay. All right. So that's all for the announcement. And let's see. Wei Xiang, good morning. Wei Yuan, good morning. Jimmy, 赵启良新人冠宇. All right. Let's go ahead and start with the section 2.2 today. So we'll be learning the first network application that is popular. So that will be the first example. Okay, so that we try to exercise all these things we learned in section 2.1, right? So we need to decide architecture, we need to decide, we need to set up a socket, and we need to define the message formats. And when we receive a particular message, what do we do next? And for each socket, you need to determine what is the port number to use, or if this is a client that you are designing, you need to also find out what is the port number of the server you intend to connect to. And you want to also know whether you want to use TCP or UDP as the underlying transport layer protocol. So we'll go through many examples this week and next week to find out how these popular applications we are using already, how they are making the decisions, okay? What their architecture is, what kind of socket they use, what transport layer service they use, and what are the message types they define, and how these messages, one might trigger another. So first is HTTP and World Wide Web. And let's start with the introductory video. Let me introduce HTTP first.
Web and HTTP. Let's do a quick review. Web is essentially a bunch of these web pages interconnected. So each web page consists of a number of objects. The base object is typically a HTML file. And then in each file embedded are several referenced objects. And these objects could be another HTML file, could be a JPEG image, could be an applet or a script or an audio file. Each object on the internet, on the web, is addressed by the URL. So this is an example of the URL. There are three parts: the host name, and the path, and the file name. And the HTTP protocol there to support the web application runs in the client-server model. So the client here are essentially the browsers. The browsers is essentially requesting for web objects and then in turn receiving web objects, of course, using the HTTP protocol. Now another task the browser does is displaying the web objects. Just to clarify, passing of these messages and web object is the HTTP protocol's job, but displaying web object is actually something else's job. It's the HTML interpreter's job. Yeah, so HTML interpreter is not quite the HTTP protocol. So you see here, a browser, that program there, is a combination of the HTTP protocol client side and an HTML interpreter. So this interpreter is to interpret the HTML page because there are some markups around. Based on the markup, the interpreter will know how to display a web object so that it appears properly and nicely. Now the server, web server, very few of you guys have experience building your web server, I suppose. Yeah, so in this example we see Apache, I think is still the most used server, but this guy here is catching up, and Jinx. Both of these servers are implemented using C and C++ socket. All right. So the web server implements server side of the HTTP protocol. So what it does is to receive requests and send back response. So that's the exact opposite of the client. It's to receive objects and send requests. So let's see the exchange. So this client up here, sending HTTP request and then receiving the HTTP response, and containing the HTTP response is the web object. Similarly, if it's a phone, Safari sending HTTP request and server sends back an object and Safari renders and displays the object. All right, so that's HTTP, Hypertext Transfer Protocol, HTTP. And HTTP runs on top of this transport layer protocol, TCP. And the whole process is actually this. First, tries to establish a TCP connection between the web server and the web client, and then sends the HTTP messages. So before the client and the server sends HTTP messages, the client and the server sends TCP messages first. So starting from the client, initiating a TCP connection. Now if this is a web server sitting on the default port, it's going to be port 80. And then server would accept the TCP connection, inform the client, and then client can begin sending the HTTP request, and the server sends back HTTP response. When everything is done, the TCP connection will be closed. Know that HTTP, as you see, very simple, request response. In fact, each of these requests is treated as brand new, it's very fresh. That means what the server is doing there is to not record anything about the client. So there's no information about the past client requests. Okay? And we call this type of a service a stateless service. So on the server side, there's no requirement of storing anything about the client. So this is really nice because the server does not require a lot of memory space for these information. Yeah, protocols that maintain states can be complex, so this is the other extreme. You might need to maintain the past history, which can be long. And you might need to maintain history for multiple clients. How about that? That's a lot of burden in terms of a memory space requirement. And besides the service load, the memory requirement, what if the server and client each crash while the other continues to run? Then the states on the two sides might be inconsistent, and they will have to resolve the conflict somehow. That's the worst, right? So should you trust the client or should you trust the server? This is one of the classic car problems, all right?
All right, so that you see, the communication model is a very simple client-server model, right? And it's using TCP as the underlying transport layer protocol. And that is the basic of HTTP. But there's something slightly complicated about how HTTP established that TCP connection. This next video is important, about 8.5 minutes long, and quiz 9 is going to be about how HTTP connects and send the HTTP messages. So let's pay attention.
HTTP connections. There are actually 3 flavors of HTTP connections: non-persistent HTTP, persistent HTTP, and third, persistent HTTP plus pipelining. All right, so let's start from the most basic, the oldest flavor, non-persistent HTTP. This is implemented in the pioneer versions of HTTP, let me call it that way. In that, you send one object per TCP connection. So the clients and the server sets up a TCP connection, and then you send one HTTP request, you get one web object, and then you close the connection right after that. So to download multiple objects, you need to create multiple connections one after another sequentially. Now in persistent HTTP, the main idea is, well, why do we keep opening TCP connections and closing them? Why don't we just reuse the TCP connection we have started in the first place? So in persistent HTTP, client and server establish the TCP connection, and then first web object exchange, second web object request, and the object response exchange, and so on and so forth. So one single connection to send all the objects. All right. Now, the basic persistent HTTP mode works more like that. So you have one exchange to establish TCP connection, and then it's just object 1 and object 2 and then object 3. Okay, but the thing is this: when we establish the TCP connection and sending out the first request for object 1, really before the object 1 is being transmitted back, you see, client over here, it needs only this amount of time to send the request message, right? Client is immediately left idle right after that. So why don't we send the second object's request, the third object's request, and the fourth object's request subsequently and immediately? That way, you just need another exchange like this, and just a few more transmission time. Then we're done with everything. Unlike here, for each object, you need this much time, and the second object will wait this much time, and the third object waits even more time. Okay, so this here is the persistent HTTP plus pipelining. Nowadays, when people say persistent HTTP, the implication is that, hey, it's persistent HTTP with pipelining. And by the way, this is HTTP, the 0.9 version. And persistent HTTP without pipelining, that's the HTTP 1.0 version. And the one with the pipelining is the HTTP 1.1 version. All right. Now let's go through the animation for the very standard non-persistent HTTP protocol's behavior. Let's suppose we are looking for this object here. So the URL contains the host name, the path, and the file name. And let's see that this base file here contains 10 reference objects. So there are 10 images embedded. Step number 1, the TCP establishment. Client here initiates connection request. Server sitting at this location at port 80 will accept the connection and then send back a sure, open it message. Second exchange is the client sending the request message. All right, so in the message embedded is the URL. So that's going to go through the socket, and URL right there in the message. Server will receive the message and sees the URL, finds the path, finds the file name, and therefore extracting content and generate the response message. And that response message is shoved again through the socket back to the client. Now, immediately after the response is sent, the server closes the TCP connection. HTTP client here receives the response, parse the HTML file, and displays it. And in that process, it's discovered that there are 10 more reference objects to download. And the client then will repeat step 1 to 5 again and again and again, 10 times until all 10 objects are downloaded. And the time to do that is Ooh, pretty long. Let's try to count the amount of time to complete the entire download. And we call that the time to download an entire page being the response time. Before calculating it, let's define this term. RTT, which stands for round trip time. It is the time for a small packet goes out to the other end and comes back, out and back. So it's a round trip in a sense. So client over here, server code over here, to initiate a TCP connection, the connection request go, connection established, granted messages come, that's one round trip time, right? So one round trip time for initiating the TCP connection. And it's another round trip time to send HTTP request and receiving the HTTP response. So this part is one round trip time. But the dark, thick square here, this is the time it takes to transmit the file. Okay. So when the object is very small, this is very narrow. When the object is large, this could also be quite wide. So we fill it up. Yeah. So the object itself could be big. The transmission time can be long. So the shadow part is the file transmission time. So the response time to download just one object using non-persistent HTTP is 2 round trip time. 1 here, 2 here, and then the file transmission time. Now we can try to account the response time for that page we were loading, the something.edu, the object there. So we have the base and then 10 more objects. So altogether 11 objects. If we're running the non-persistent HTTP connection, then we have 2 round trip time plus the transmission time for object number 1, the base object. For each of the 10 objects, we do more. Okay, so the transmission time might vary a little bit from object to object, but round trip times remain the same. All right, so there are 10 of these. So 22 round trip time. So 10 of these plus this one over here, the base. And yeah, the sum of the TX. Okay, and depending on which object it is for all I. All right. Now, but for persistent HTTP, the server is going to leave the connection open after sending response. So subsequent HTTP messages between the client and server will be sent over the open connection. Client can send requests, as I said, right? Persistent HTTP without further clarification, it's the persistent HTTP with pipelining. So the client here will send all the 10 requests as soon as possible. Okay. So in the end, it's just 1 round trip time plus the transmission time of all these objects. So altogether, just 2 round trip time. First is to establish the connection. Second is to download the first object. Okay. Third is to download all the rest of the 10 objects. So it should be 3 round trip time plus the transmission time required to send all these objects. So 22 versus 3. Big win over here, right? Yeah. So this is in HTTP version 1.1, the most up-to-date version.
Okay, good. So that's exercise calculating the response time. How about that? So quiz 9 here is tell the response time in terms of RTTs to download the web page, where you have one base HTML, and the client here, after receiving the base HTML, then discover that there are 5 reference objects that the client needs to download further. Okay, so you need to get the base object first, and then the 5 reference objects after you receive the entire base object. Okay, so for the simplicity, let's ignore the transmission time because we know the transmission time part is fixed no matter what kind of connection mode you use. Okay, so tell me, what is the response time in terms of RTT in Q1 using only non-persistent HTTP connection? Q2, persistent HTTP connection. Okay, so this is by default with pipelining. And Q3, how about persistent HTTP without pipelining? And 4, what about non-persistent HTTP, which is the original HTTP, right? The 0.9 with long response time HTTP. But how about for the 5 reference objects, we start 5 parallel connections to get the 5 reference objects at the same time. I remember yesterday, I think I forgot exactly who, some student asked, can we start multiple sockets in one application? Of course you can. So here I'm asking you, one persistent HTTP connection, using non-persistent HTTP connection mode. After you get the base object, start parallel connections to get the rest of the reference objects. Okay, so how would the response time be like that for Q4? All right, so let's go to quiz 9 on Slack. Okay, so you have about 5 minutes time to think about this. Okay, for the first 2 Qs should be straightforward. Q3 and Q4 might be a little bit tricky. Okay, and the first solve the problem gets a yellow mark on the quiz grade. All right, go on, start. I think you guys have already got it. It's quite straightforward. So I see that Q1, all of you, team 3, team 1, team 8, Keke. Oh, actually, more teams are typing up their solutions. Yeah, great. So I think Keke, thank you, because here Keke is showing team 10's derivation. So exactly, you have the base HTML, and so for the first TCP connection here, you open it up and get the first base object, and you need to close it, right? And so for the rest of the 5 objects, you need to do it again. So altogether 6 connections to get 6 objects, and one after another. And so you need to get the base first, right? So 12 round trip time for non-persistent HTTP. For persistent HTTP with pipelining, set up TCP connection, get the base object, and you can have the TCP connection on without closing it. Therefore, for the rest of the 5 reference objects, you could actually send requests back to back, right? And then get all of the 5 objects back. So how many round trip time? 2 round trip to get the base, and just 1 more round trip to get all the other reference objects. So 2 round trips, first to establish a TCP connection. Now you see, yesterday some of you were asking, right? Why is TCP slower than UDP? Because UDP doesn't need to do this, setting up a connection. And requests, HTTP requests go, HTTP response come back, 1 round trip time to get the base, and then 1 round trip time to get all the other reference objects pipelined, one after another. Okay, so in this round trip, 5 requests to the 5 reference objects will go out, one after another, and transmission time usually much shorter. Back to back go, and then objects coming back to back as well. What about Q3? Persistent HTTP but without pipelining. Well, it's persistent HTTP, right? 1 round trip to establish a TCP connection, 1 round trip to get the base so that you know that there are 5 reference objects. And what do you do now for the 5 reference object? How do you fetch these? Well, you cannot pipeline them. So you cannot send 5 requests back to back. So you need to send 1 request to get the first reference object, and then the request for the second object. And so you have 5 round trip time there to get 5 reference objects back. Okay, but still, nice thing is that for persistent HTTP, you don't need to start another TCP connection for each of the reference objects, right? So you see, in the end, we have 7, 1 to start TCP connection, 1 to get the base, and 5 to get the rest of the 5 objects, together 7. And so you essentially save 5 round trip to open the second TCP connection, the 3rd, the 4th, the 5th, and the 6th, right? So you see the diff of Q1 to Q3 is 5. The last one, Q4, non-persistent HTTP with parallel connection. Well, now we have to close the HTTP once the server sends the object back. Okay, so for the base object, obviously set up TCP connection and get the base object back. But server is going to close the connection. Here at the client, we see we have 5 more reference objects to get. Okay, but we now can have set up parallel connections. So we could have 5 connections set up at the same time and send the request at the same time. But you know what? To set up 5 connections and get the object, 1 round trip time for the connection to set up, 1 round trip time to get the object back. Even though the 5 objects, we set up 5 TCP connections in parallel. So completely in parallel, that would be what? Still, everyone set up a TCP connection. Every one of these 5 send HTTP requests, get HTTP response. So you have 2 round trip time there to get the rest of the 5 reference objects. So 2 round trip time for the base object, 2 round trip times to get 5 reference objects in parallel. So 4 RTTs. Nice, isn't it? I do see Team 1 is saying something a little bit special about Q2. You know what? Team 1 is also correct. Okay, it might not be necessary to take 3 round trip times in the persistent HTTP mode to get all the objects back. Okay, this happens in this case. Okay, so if the reference object, if the base object is coming back and the reference objects are actually at the head, at the beginning of the reference, at the beginning of the base object, some router can actually see the reference object, okay, and start fetching the reference objects. Because the connection we already set up for the base object, it's open, right? There's no other request being sent. So once the browser discovered that from the base HTML, although the downloading is not exactly finished, it can actually started fetching the reference objects a little bit earlier. Yeah. So one can potentially finish everything less than 3 RTT. Yeah. All right, so good. 12374, you've got it. Very good. Yeah, all the detail. 223, okay. Team 2 also is convinced that in some cases, some browser, okay, will be able to do that. That is also why sometimes you see a web page that there's like an image in there. And as the browser rendering the rest of the page, it renders in parallel part of the image as well. So some of these browsers being implemented, they can do multi-thread or concurrent programming so that they can do parallel, seemingly parallel downloading. Okay, as you guys go on to PA6, you will see in many of the modern programming languages, to do this, it's not entirely difficult. It can be quite straightforward in the newest programming languages. Okay, very good. That's all. You've got it. This is HTTP connection. It has multiple flavors. And now let's move on to the next topic. So we've talked about the architecture of HTTP. We talked about socket, it's TCP, and it's connecting to port 80. But exactly how you keep the TCP connection, it depends. And then, we have not yet talked about the messages, right? Types of messages defined and format of the messages. You know what, in HTTP, there are only 2 types. And let's start by talking about the format of request message. Let's take a closer look at the syntax of HTTP request message. First is the request line. It's only a single line, 3 tokens, separated by 2 spaces, one over here and one over here. First token indicates the command the client is issuing to the server. So get here is the most classic command. Second token here indicates which object the client is wishing to download. So here you see the path and the file name of the object. Third token is very straightforward. It's simply telling the server the version of the HTTP protocol the client is implementing. Now, header lines. Syntax is also quite straightforward. Column in the middle. Before the column, this is called the attribute or the field name. And whatever comes after the column is the value of the attribute or the value of the field name. All right, so user agent is a well-defined attribute in HTTP. It indicates what implementation the browser is and the version of it. So user agent indicating the meaning being user is using a browsing agent called Firefox, and it's version 3.6.10 of Firefox. Okay, similarly, okay, keep alive, also a predefined attribute. And the value 115 is saying that let's keep the connection alive for 115 seconds if there are no messages being sent. Connection indicates the type of connection the client is wishing to establish. It's the keep alive kind of connection. And so you see the syntax and a little bit of semantics of HTTP request. All right, so that was the request message. But let me come back up here to answer Wei Yuan's question. Okay, so I'm a little confused about the difference between pipelining and parallel connection. I hope that after we went through quiz 9, then you understand the difference between pipelining and parallel connection. So parallel connection is to have multiple TCP connections starting at the same time. Okay, but pipelining is you use that TCP connection and you send all 5 requests in that TCP connection. Okay, and let's come back here, request message. This is a back-to-back quiz. The quiz number 10 here is to ask you to exercise the video you just saw. Okay. Oh, this is the HTTP request message format. It's very straightforward. It's showing in text mode. All right. So let's see in quiz 10. Consider, again, text file captured by a tool called WinDump. This WinDump can capture actually packets going through your network interface. And then we capture this, an HTTP GET message. And this is the detail of the message, get/cs453, etc., etc. All right. Q1 asks, what is the URL of the document being requested with this message? And why do you know? Q2, is it a non-persistent or a persistent connection being used to send the request? And how do you know? This is supposedly a very straightforward question. You have only 2 minutes to think about it. And so let's go to quiz 10 Slack space and work on it. All right, I see team 1 here. Let's see. Okay, the URL is gaia.cs.ums.edu. All right, I see. So URL is the host name and the path and the file name. So you see the host name by looking at, host column, isn't it? And the path and URL is in the command line, get, and then the path and file name. Very good. And the connection is persistent because, so there's the connection type is keep alive. And it keeps the TCP connection alive for 115 seconds. Let me see, is it also here? Oh no, for this message, the client is asking the server to keep this TCP connection alive for 300 seconds. And Jia Hong, representing team 5. Yeah, you've discovered the same thing. Very good. So you guys get the idea. The format is actually quite straightforward and it's text-based. Now there are specific fields. One needs to see some reference documents to know exactly what they meant. But what we went through in the video was very commonly used field name. Right? Good. So it's quite straightforward. I'll let you guys work on it offline. And let's move on to the next video. So for the command line, the command we're seeing is get. But get is not the only command one can issue to the server. Get is to download a HTML object or any reference object. But there are other commands, for example, put, to actually put objects onto the server. So what are these commands? Okay, we call them the methods as well. So that's the next video.
And the last slide about HTTP request here is quite straightforward. What it says is to tell you again what are the comments, okay, possible in HTTP request line. In version 1.0, we see get, we see post, we see head again. But this is all that HTTP 1.0 supports. In HTTP 1.1, we extend the comment options from the 3 classic ones to add 2 more, put and delete. Okay, let's go through these 3 other comments. First, the head comment. So this is usually for a web client to send sort of initial HTTP request to the server, and server will send some response back, but only to tell the status of the server or the specifications of the web server, and leave the actual web object the client is asking for out of the response, so that the response is very short. And what's contained in the response messages are just all the essentials, like, what is the version of the web server program you're running over there? What is your IP address? What is the time date? What is the time date, the object that the client is asking for being modified last? Okay, things like that, the essentials about the server, about the object, so that when the client receives a response like that, the client can plan a little bit better ahead of time how the client does the requesting. Sometimes when the file is really large, the client might try to dissect and then do the requesting slightly different. And put here, this one is actually quite forward, just to upload the file in the entity body of the HTTP request to the server, right? So in that request, we also specify which path in the server we want to upload this file to. Okay, so it's working pretty much like the FTP. If you recall FileZilla, you are dragging a file to the server, right? So it's uploading a file to a specific path on the server side. So put here implements file upload. Delete, deleting a file. So FileZilla also allow you to do this. So essentially, HTTP 1.1 is to extend the original HTTP to include all the file uploading, downloading services, because the original HTTP only does file downloading, not quite the uploading. Now, when HTTP 1.1 is available, FTP protocol quickly loses its popularity. Okay? And that's why we rarely use FTP these days, because HTTP, the web browsers can do all these for you. All right, so this is HTTP request.
Right, and that takes us to the next message. After sending requests, server generates these response messages, and the video is slightly long. Okay, I think some 7.5 minutes. Let's follow the video also closely, because quiz number 11 is coming up. So we do have back-to-back quizzes the first hour. But it looks like we might not have enough time the first hour. So what I'm gonna do is I'm gonna play the video, and we'll end the lecture. I'll post quiz 11. After the break, we'll come back to look at how you guys answer quiz 11. So now the video.
Now, finally, the HTTP response message. Okay, the second type of messages defined in the HTTP protocol. You see here, generally, 3 parts. First, the status line. Second, the header lines. And the third, the data. So the entity body, so to speak, from here and down. Okay, and these are very similar to the header lines we see in request message. Each line, you see attribute and the value. Attribute and the value. Status line. 1, 2, 3. Again, 3 components. Let's go through each one of them as well in a bit more detail. In status line, first here, familiar. So the version of HTTP the server is implementing is the first component. in the status line. Second, this is the status code. So in HTTP, it defines quite a number of these status codes. Each of these indicate a different condition. Some more related to the server, some more related to the object being requested. And for each of these status code, there's a status word being shown as well. That's the third component in the status line. So 200 here indicates OK, meaning the HTTP server is working well and the object you're looking for has been found. And it's going to come here in the body entity. Now, second part, the header lines, we see date. Yep, this is the date, time, the request is being filled, and this response is being generated. The server, this is an Apache server, version 2.0.52. Apache is one of the most commonly used web server implementation. Yeah, I think you heard about the other one, Nginx. So Nginx is certainly rising. Okay, it's not quite yet the most popular one. Well, let me clarify. By popularity, I meant the number of machines running a specific version of web servers. So Apache is still the most used web server. But if you count only the number of downloads recently, it might be Nginx. That's why you see I say that it's actually rising. So I think maybe in just a couple months, there'll be more Nginx server than Apache servers. Last modified. Yeah, so this is to indicate when is the object you're downloading last modified. Oh, okay, it's a really long time ago. All right, e-tag. What is this? This is actually, hey, for each version of the object that you are downloading, there comes also with a version number. So e-tag there is to indicate the version number. Nowadays, as you see, the HTTP protocol is not used only for downloading purpose. It can also be used for uploading. If there are multiple users there using different web browsers trying to upload the file, for example, Poly and Caleb, the TA, tries to upload and override the grades Excel file, then you might have a consistency problem there. So the number here is to break time, to make sure that a newer version does not override an older version or something like that, to resolve conflicts, so to speak. And accept range. Yeah, yep. So, you know what? Earlier when I mentioned the head comment in the HTTP request message, right? So when you send such a comment in the HTTP request message, the server responds with only the status line with the header lines, but without the data. Okay? So server there can actually tell the client, you know what? I'm a server that allows you to request content in terms of bytes. So the client there seeing this can then send a request more officially instead of using the head command, using the real get command and request to download byte 0 to maybe 1023 or byte 0 to byte 100. Okay, so you could do a range request in a way. And the server's next header line, content length. This is to indicate the size of the file or the size of the object that you're downloading. So you see the file size of the object is one critical parameter. Okay? If you're implementing a web server, you need to know a way to find out what the file size is or the object size is. Okay, the size is a bit messy. Let me clear the markups. Keep alive. Oh, good. This web server implements persistent connection. Okay, and so it indicates timeout interval is 10 and maximum 10 requests. So this is a persistent connection, but in the connection, it only accepts up to 100 requests. All right. So if it's more than 100, then you will force close. The server will force close the connection. So connection, keep alive. Content type. Yeah, just like the client size header line we see. Yeah, the client accepts content of a certain format. Here, okay, this is to indicate the object the client is asking for, which format it is. And we see this is text-based HTML file and it's coded in ISO ep08. Right? And empty line, indicating this is the end of the header lines. right after the empty line, the data goes here. If it's an HTML file, then hey, text starting from here. Okay, the first file. So this is an example of HTTP response message. You see the structure is very much like the HTTP request messages. Next is just to share a bit more. HTTP response messages status code. We've seen earlier in the example 200 OK. This is saying request is successful, object is already embedded. 301, that means the server is saying the object is moved to a new location specified later in this message. So sometimes when you run into a message like this, you see, oh, click here. That's going to take you somewhere else. It's a redirecting link. If you see status code 400, that means your HTTP request format is not quite correct. Bad request. 404, that means the object you are asking for is not found. 505, HTTP version not supported. So in case you're using a very, very, very old browser, or if you're contacting a server that's very, very old, and yet your browser is implementing something newer, then you might not be able to communicate. The server is going to tell you this. Sorry, 505.
All right, and this is quiz 10. So let's take break in the meantime. It's very similar to quiz 9. Actually, sorry about the label, or is it? Oh, okay. I can fix this right away because quiz 11 is not this side. Okay, give me a second. There we go. So this is quiz 11. Okay, so we intercepted a response message this time. And I'm asking you, can you tell whether this object or this response message is indicating whether the download is successful or not? Q2, how many bytes? Okay, if it's successful, how many bytes are in this download? And Q3, what are the first 5 characters in this file being downloaded? All right, so break. It's 11:12. Let's come back at 11:22. The question is also posted on Slack, so feel free to go to Slack and start working on it. Oh, wow. Okay, yeah. Now with the quiz 10 being done already, you guys pretty much get the idea of the message formats of HTTP. Very good. Yeah, so let's take break in the meantime. welcome back. So Catfish does have a question. I think this is a very good question. Does the browser interpret... Oh, wait. Hey, I think something is wrong here. The chat channel is not really updated. So give me a second. Let me update it here. There we go. Yeah, so you guys might be wondering, how come Polly is saying that someone asked a question, but it's not showing on the chat. All right, now you should all see the YouTube chat. Okay, and you now see Catfish's question. Does the browser interpret the web page after receiving all the reference objects? You know what? It really depends on the browser implementation, Catfish. Some browsers will actually finish downloading the whole base HTML before starting to interpret it. Okay, but some browser might be able to start interpreting the base page and discover there are reference objects. So I think Catfish, there's another term called rendering. Okay, so interpreting the web page, one can start doing it after we receive messages from the server. Okay, but rendering the page is something else. So when a browser can interpret the web page and just partial base page, and then start rendering, start drawing what the HTML page should look like on a web browser, okay, or a picture should look like on a browser. Okay, so these can actually all go on. Messages arriving. Web browsers start interpreting, and after interpreting to some degree, start rendering. Okay, so data in, interpretation, rendering. And this can also be pipelined, you see. Partial data arriving, partial data being interpreted, and partial data being rendered. So a browser can be rendering a page as the files are still coming in, or the reference objects are coming in. So the browser can be interpreting the files is coming in, the base object, and then discover that they're reference objects. So on one hand, start drawing the main object and requesting the reference objects. So all these things can be done like in a concurrent way. And in fact, this is more modern browsers do, because it would appear it's seamless. You started seeing something showing already while the network is busy sending file, and the browser engine is trying to interpret the HTML. Usually the users feel better because it starts seeing, oh, something is being drawing on the screen. So you don't click reload too quickly. All right, so that should address Catfish's question, and we can move on to demo. Okay, so Polly is going to show you how to send message and receive a response, and seeing the content of request and content of response using this thing called telnet.
So what I will show you in the demo coming next is to do this. Telnet to the favorite web server here, and we're going to use this machine here that the textbook author has set up for us. So we'll telnet to gaia.cs.umass.edu at port 80. Okay, what it does is to open the TCP connection to port 80, where there's a server already running, a web server already running. And anything typed in will be sent to port 80 at this guy. Okay. So telnet is a remote logging application, just like SSH or RSH, if you know what it is. It's another remote logging command for native Unix users. All right, so telnet is very, very old. Many operating systems probably doesn't support it anymore, but I've already installed it on my Mac, so we're going to show that thing a little bit. Now, once we telnet to the web server, and we'll type up some things. Okay, let's try typing this. Get path name and file name as the argument for the get command, and then the version of the web browser. So we'll be pretending that the telnet here is a HTTP 1.1 client, and host gaia.cs.umass.edu. Right, so header line. So essentially, we are trying to do a human web browser, okay, by typing online right here an HTTP request message. So once we are done with this, we hit return, okay, and then we hit return again. It needs to have a what? A \r\n here in order to complete the HTTP request. All right, so the whole thing is going to be like this. And yeah, we'll see what pops up in return, what the server there at umass.edu sends back. Okay, let's not sniff the traffic. Let's just look at the response coming out of the telnet program. All right, so let's switch to the demo mode. All right, let's telnet to gaia.cs.umass.edu at port 80. All right, connect it to gaia.cs.umass.edu. Now let's pretend to be a web browser. Get. Oh, wow, that's pretty long. The patent file, pretty long. Let's copy it from the slides. And over here and print. All right. And then host poly.ntu.edu. How about that? All right. And one more empty line to indicate this is the end of the header lines. There we go. Wow, it's returning a lot of things. Scroll back, and scroll back. Wow, very long, in fact. But it looks like it's an HTML file, right? It's an HTML file. This is a hyperlink to an text HTML file. Okay, let me scroll a bit faster. I don't know how long this is. Oh, there we are. Yeah, so we typed up this line here. Okay, and we also say we are host poly.ntu.edu.tw and an empty line and then return again. The whole message gets out to the web server at gaia.cs.umass.edu, and the web server returns this http://11 to the 200. Okay, and header lines number 1, the date. Header line number 2, the server. Oh, it's an Apache server. X powered by PHP. I see. Content length, content types. And hey, empty line to indicate this is the end of the header lines. And starting from here, the real body. Okay. So we get the output of calling this PHP query at this path. Let's see, interactive problems, computer networking, a top-down approach. Oh, okay. So this looks like the main page of all these interactive exercises that we see every now and then on the slides. All right. So there, essentially very text-based interaction between the client and the server. As human beings, we could also do it right here, right now, online as a web browser. All right. And I think let me just go back a little bit here. You see here, 200 is a very classic example of the syntax defined in an application layer protocol. In HTTP, to be exact, 200 is to indicate OK. So OK here is just to say it explicitly, the semantic of 200. Right? So that concludes the messages format, semantics, and syntax of HTTP.
So finally, we finished talking about the HTTP protocol. But it's not all. I think Xuehan asked the question that HTTP is stateless. Why do we need to mention that? Because it's actually a special characteristic of a protocol. It's very simple. But next thing we'll talk about cookie. It's actually to make HTTP stateful because in some cases it's more convenient for the users to have the states, to have servers keeping the states, to have clients also keeping states. So let's hear out cookie.
Next, cookies. Yeah. Many websites these days will try to prompt you to set up cookies before they allow you to visit the website further. So it's very, very relevant to our everyday life. Let's see how it works. Okay. First thing is, the cookie setup process is always initiated from the website. So meaning from the web server that your web browser is requesting objects from. So web server there is going to send a message to the web browser carrying a special header line. Okay, it's the cookie setup special line. And the web browser there, upon receiving such a message, it's going to generate a corresponding message if you click OK to insert cookie. And that message is going to carry, again, a special header line saying cookie OK. All right, so exchange of messages between cookie setter and cookie allower. Now, when you say, OK, I will allow setting of the cookie, your browser is going to add an entry to the special cookie file on your local disk. Okay? So that is exactly what's expressed here in the special cookie setup line. And when the server receives the message allowing cookies, server would then add a special entry as well to the backend database. And that entry set up here and here will actually map to each other, allowing the server to identify who you are and when have you visited the website last time. Okay. Let's use an example to explain. It will work slightly better. Let's say Susan always accesses internet from her PC. And she's visiting a specific e-commerce site the first time. In the initial HTTP request, that arriving at the server, the site will then create a unique ID. Okay, and that will be an entry being added to the backend database. Right? So that ID is going to be carried. Okay, in the message, the site sends back to Susan. So that's going to be set cookie and then the number created here. All right. So local hard disk you have there, or Susan has there, will have that entry set up in the cookie file. So this will go back to the server. Okay, carrying also that special ID that Susan has already allowed to set up. And then at this point in time, the server would finally enter the entry to the backend database. So that's the way it works. Let me illustrate, and so that you know clearly what's going on. Client, server, or Susan, Amazon.com. Now, at the client side, you have this special cookie file, and it's managed by the web browser. And you might have clicked OK to eBay. So eBay has already set up a cookie entry, carrying unique ID ep08. Server here has a local disk as well. It's maintained more as a backend database instead of just a simple file. Right? So, but when you visit the website, Amazon.com the first time, you send an HTTP request message. Now, of course, you have not yet been in Amazon before, so there's no entry for the Amazon website. Okay, so in your initial HTTP request message, there's not going to be any cookie special header lines. All right. So when Amazon.com here receives HTTP request, of course, it will try to grab the objects that you're looking for and try to generate the HTTP response with it. But in the meantime, it will be creating an ID for this particular user. And add that to the database. And in the response, it carries the web object that you're looking for, but it also carries the special header line, the set cookie line. And hey, see, the ID created is carried over through the HTTP response message back to the user. So, web browser here sets up one extra entry saying, hey, for Amazon website, use ID 1678. So for the subsequent visit, subsequent browsing, all the HTTP request messages is going to carry the cookie OK and I am a user 167A header line. Right? So here the server, of course, will be generating the web objects, generating the HTTP response message that you're requesting with the request message. So response message. But the response message might also contain additional content. Okay? Server there could be seeing your browsing history a couple clicks back and discover that, hey, you might be looking for a specific item. okay, and then recommend potentially items you'll be interested. Okay, so that might also be part of the response messages. So showing the items you are looking into buying as well as related products. Okay, so for example, if you're looking to purchase a phone, then the website might be recommending a phone case, okay, or a number of phone cases. So what's amazing there is 1 week later, okay, when you come back and try to purchase something from Amazon again, okay, the first request message you'll be sending will already be carrying the cookie entry. Okay, so once you have it set up locally on your cache file, on your cookie file, for all the subsequent HTTP requests, it's gonna by default carrying the cookies. Amazon here will know, yeah. So over time, the server will know probably your profession, probably your income level, things like that. Okay, so that's why it gives people a certain creep about setting up cookies, and you might be warned, be careful about setting up cookies there.
That's also why nowadays, when you go to a specific web page, they ask now more explicitly whether you are okay setting up the cookies, or they ask explicitly what cookies you allow for that website to track you. So you see that the cookie being stateful is convenient, right? Because as you are browsing, the server side can actually recommend things that you might be interested in, and making it easier for you to find the stuff you're looking for. But it can also be a little bit intrusive. So there's a certain trade-off using cookie.
Now let's discuss cookies a bit more. We're going to talk about the trade-offs of using cookies. First, the cookies from a business perspective, from a website's perspective, is actually quite convenient. So you see, you can authorize the users quite easily, okay, by looking at the ID in the cookie header line. Tracking the shopping carts as long as the ID is the same, right? This is items purchased from the same user. You can recommend items so that the users will go, wow, cool, that is exactly what I was looking for next, right? If the user is purchasing a phone and the website suggests purchasing of a phone case. Yeah, and browsing emails, yeah, you will not want to try to log in and type up password again and again. You want to be able to maintain that email reading session, email sending session over time and log in just once. How? Very nicely through the cookie line in the HTTP request. Okay, quite convenient. Okay, otherwise, you guys, including Polly, when I read my Gmail, I have to log in again and again and again. There's no way we could live like that. Right? So convenience. But on the downside, those websites will be able to learn a lot about you. Okay? So you store emails, that's pretty much your personal life. You store your purchases there, that's pretty much also your personal life. Okay? So over a long time, you can imagine Google, Amazon, Facebook, all these major websites, they know a hell lot about you. That's why people are freaked out so much about these big sites, okay? Allowing them to set up cookies, allowing them to store information about you, okay? So downside, privacy. Okay? Now, another perspective is more technical, keeping states. Now you see, hey, there's ID on the local cookie file. There's ID stored at the server side, the backend database. So server and clients are now storing states of each other, about each other. But some of you might go, hey, wait a minute. Didn't we talk about HTTP being a stateless protocol? And what's nice about stateless protocol is that, hey, none of the endpoints need to store anything about each other. Okay? No storage requirement. And you don't have this problem where, hey, if the connection between the client and server is broken, and you might have these inconsistencies in the states they maintain for each other, right? You have to reconcile and resolve conflicts. And that is actually a very, very hard problem, okay? Who do you trust more, the server or the client? Okay, sometimes it's a bit hard to say, okay? So cookies here, you're seeing is, in a way, a hacking HTTP such that we can maintain states, because HTTP was not designed in the first place to maintain states. But then now with the cookies, we have this issue potentially between the client's cookie file and the server's backend database. What if, the entry is inconsistent? Then you might have an issue as well. So trade-off in terms of usage, okay, in terms of privacy concern. Trade-off in terms of technical difficulties maintaining the states.
All right, so, well, let me know whether you prefer having the cookies around or not. Okay. While you are thinking about it, it's time that we move on to yet the next topic called the local cache and web cache, or caching in general. So caching is used a lot to try to improve the efficiency of using data-oriented services. Okay, so let's hear out what local cache does for HTTP.
The next two topics are more about trying to reduce traffic between the server and the client, or trying to reduce the delay downloading a certain object. It's called the caching. So what cache means is to store a temporary copy of certain data. Okay, so conditional get here is like to have a local cache of the web pages that we have downloaded previously. Okay? So the goal is to not send the object again and again and again if the copy we're storing here is already the latest. Okay? Because as a result, we don't need to send the object, and that reduces the delay, and we also reduce the bandwidth requirement. Okay? And so saving the bandwidth is going to be good for everybody. So the way it works is this. So the first time the client downloads a web page, it's going to keep the copy of the web page on a local cache. So that's somewhere in your local disk. And in the meantime, we record the date, okay, the cache copy is downloaded. And so that when we send a request for the same page again, we carry this special line in the header field, the if modify since, and then the date, okay, of the cached copy, the day we have requested the copy the first time. And then at the receiver side, at the server side, the response will contain the no object if the cached copy is actually the most up-to-date, meaning if the copy at the server has not been changed after the date, then there's really no need to send it again back to the client, because the copy right here is already the latest. So in that case, a special HTTP response message is going to be sent, and the status line is going to read like this. 304 not modified. And in the body of the HTTP response message, it's going to be empty. Okay, so no need to send the object. And the way it works is more like this. Let me illustrate. The second time, the client here requesting for the web object sends request message and having this in the header line. If modify since the date the page was downloaded the previous time. And if the server finds that no, it's not yet modified, then send back a short HTTP response carrying the status line. And that's all. No data here. But otherwise, if the object is modified, then we send back a regular HTTP response that says 200 OK in the status line and the web object, the web page again, okay, in the body and the T.
All right. With local cache, you still need to send the message all the way to the server, and the server send the response back, right? Even though it does not really need to contain data. But this next one, called web proxy cache, can actually save you some time traveling the internet. Okay.
Web caches. The purpose is very much like the local caches, but the way it works is somewhat different, but not much different though. The main difference is this. In local caching, we keep a copy of the object here. Okay. But now we keep a copy of the object here in the web cache, or also known as the proxy server. Web cache or proxy server. Okay. And in conditional get, we still need to send HTTP requests to the original server. It's just that the original server decides whether to send the object with it or not in the response. Okay, sometimes yes, sometimes no. So we save a little bit delay and bandwidth this way. But in web caches, the goal is actually trying to satisfy some client request such that there's no involvement of the original server required. Okay, so some of the clients doesn't need to reach the original server to get the object. And this is done by keeping a copy of the objects somewhere in the middle at the proxy server. Okay, so the way it works is this. Users will set the browser such that for all web access, let's go through the web cache. So subsequently, the browsers will send all HTTP requests to the web cache. So send it to the web cache. If the object, the page we're looking for, is already in the cache, proxy server sends the object back. So you see, it works somewhat like a server, but it's not the original server. It's somewhat a delegate of the original server having a copy here. Okay. So object in the cache, cache return objects. Otherwise, the cache here, the web cache here, would request from the server a copy of the object. So this request will be like, the proxy server here behaving like a client of the original server. Web cache there, request object from the original server like a client. Okay. And after the object is downloaded here, the proxy server then sends the object back to the requester. So let me illustrate. If the object is not here, request go to the original server, response comes back, store a copy, and then forward it back to the client. And what's nice about this is, look at this client down below. If the client is requesting the same object, it's a hit here at the cache. Server here sends back the object directly without going through this segment of the internet. So, cache there acts both like a client and a server. As a server, so that it served the original client, the objects. As a server, because if there's a miss, it will be requesting the original server for a copy of the object. Right? So, some of you might see already, right? A web cache like that is actually preferred by the ISPs, okay, which serves a whole bunch of customers locally. Usually people sitting close to each other tend to prefer fetching or tend to fetch similar content. Okay? So a lot of times ISPs might encourage you to set a web cache on your browser. Now let's go through a few examples to detail why using web caching. Local cache, nice, reduce delay, reduce bandwidth. Through this set of example, let me take you through what is the benefit of doing web caching. In a nutshell, a lot more delay and a lot more bandwidth saving.
So, the first scenario.
Good. The example. Setting is this. Servers up here, client down here. So they're part of the institutional network here. And the servers are connected to the public internet. And the internet connects to the institutional network through an access link. Let's assume that the clients here are browsing the web, requesting objects down from the server. The average object size being 100 kilobits, and the average request rate being 15 objects per second. Then multiply the two, you get the average bit rate coming down this way. Right? And that is 1.5 megabits per second. Now, let's see. Round trip delay from the institutional router to any of the origin servers and back. That's set up to 2 seconds. And the link, access links rate 1.54 megabits per second. And the local area network link rate 1 megabits per second. Now with these, we will be able to calculate the local area network's utilization. 1.5 meg divided by 1 gig, that's 0.15%. But here, 1.5 meg divided by 1.54 meg, that's very close to 99%. And that is a problem if you recall. There's this component called queuing delay in the internet nodal delay. For transmission over a hop, there are 4 components: processing delay, queuing delay, transmission delay, and propagation delay. And the queuing delay is very sensitive to the utilization on the link here. Right? So let me take you here. Queuing delay. Just in case you kind of forget about it. It's very case dependent, and the determining factor is the utilization, which we call back then when we were talking about internet delay, the traffic intensity. So this is the amount of input, and this is the output capacity. You see, utilization again. When this is very small, queuing delay also very small. But as it approaches 1, delay becomes large. When it exceeds 1, delay is actually approaching infinity up here. All right? So close to 1, close to 100% delay, just very long. Let's come back here. Therefore, if we want to calculate the total delay of web request and object download, it will be round trip delay here, plus round trip delay here, plus round trip delay here. 3 components: internet delay, access delay, and LAN delay. Internet delay, we already defined it. Just make it simple. Just say that it's only 2 seconds. But hey, here, fully utilized link with high queuing delay, it's going to be very long. Let's just say that it takes minutes. It could be even higher. And the LAN access delay, now this is very low because utilization is super low. So let's say microseconds, right? So 3 components, which one dominates? Yep, queuing delay on the access link dominates. So bottleneck where? Here, in terms of delay performance. How do we fix this? Let's look at the second scenario.
All right, the second scenario.
In scenario 2, let's try to address the issue here, because this is the bottleneck link where the delay came from OC. And let's blow it up 100 times. How about that? So using a fatter access link there. The result is that the access link utilization is also reduced 100 times. Less than 1% utilization, you can imagine the queuing delay being very, very short. That brings this component of the delay down to milliseconds. Now, why a millisecond? If you recall trace route testings that we did earlier in chapter 1, right? What was that? Quiz 3 or quiz 4, isn't it? Yeah, most of the delay we see between 2 routers are what? Tens milliseconds and maybe 100 milliseconds at most. So if there's not going to be much queuing delay, yeah, the delay is at this scale. So 2 seconds, milliseconds, microseconds, which of these 3 components dominates? Obviously, 2. And from scenario 1, we have minutes of delay, to scenario 2, we effectively bring down the total delay. All right, great. Is there any catch? If you think about it, hey, bringing the access link capacity up 100%, that is actually not cheap. So increasing access link speed, no, not cheap. You need to purchase the new cables, of course, but you might also need to do groundwork. Okay, remove the old cables, install new ones. Just think about the labor cost there. And in addition to that, you might need to upgrade the routers there connecting the high-speed link, just so that you can accommodate potential traffic volume. So, yeah, very costly. Now, in scenario 3, let's see if we could introduce something else instead of blowing up the capacity in the bottleneck link. In scenario 3, instead of blowing up the access link, let's install web cache here. I'm calling it the local web cache because we are very close to the clients. All right. Oh, and yeah, I meant local web cache here. Okay. So that you are not confused with the local cache we've talked about in conditional get, where that cache is actually very, very local on the hard disk of the user. So we are only slightly local here. So it's good. So everything else stay the same. All we did is just install the machine. Now, if I ask you, changing this to 154 megabits per second versus adding a server machine, which one is more expensive? Yeah, you probably guessed, right? Labor costs, routers are expensive, cables sometimes can be expensive depending on the distance between the physical distance between the 2 routers. For your information, this could take millions of new Taiwan dollars. But installing a high-end server machine, it only takes this much new Taiwan dollars. So that's about 2 order of magnitude difference. Yeah. Installing web cache, so much cheaper. Great. Now, let's see if the delay is also going to be better. Or maybe if this is cheaper, then delay is going to be worse. Now, let's try to calculate this. We know the LAN utilization, and so maybe the LAN delay is also about, microseconds. But access delay, well, we'll have to know the access link utilization in order to estimate the access delay. Therefore, question mark, therefore we couldn't quite yet estimate total delay, right? But then, so this has something to do with the traffic that needs to be brought down this way, right? How many objects will be coming down this way? That seems to be the question. And if you think about it a little bit more, isn't that depend on, for all these web requests we send to the proxy server, how many of them are going to be satisfied locally? Therefore, we could just, transmit the object from the web cache through the LAN to the client without going all the way up to the servers. So that is this thing called the hit rate. Okay, amount of the proportion of the requests being satisfied locally, that's the hit rate or the success rate. Yeah, let's suppose the hit rate is 0.4. Then we see 40% of the requests will just stay here. Only 60% goes out and back. Great. So we know then the access link here, the utilization is 60% of the access link, 60% of the scenario one. And how much is that? 60% of the traffic, then it's only this much traffic on the 1.45 megabits access link, only 58%. So we cut the utilization from 99% to 58% if we ended up having this hit rate. Now let's calculate the total delay. So 60% of the time it's going to be long delay all the way to the server and back. 40% of the time just on the local LAN. Now, local LAN delay, we've seen earlier, microseconds, but I'm using the milliseconds here just to take into account the traffic here. So if we go out, request object down to the web cache, and then web cache serve the local client, we have one copy down here and another copy down this way. So the LAN here, the traffic potentially could also be higher. So let's use milliseconds just to be safe and take that extra traffic into account. Now, for the 60%, we'll have to go out and back, right? So this is very negligible. This part is what? The key component. This part, 2 seconds, we know for sure. So what's remaining is just the delay here on the access link with 58% utilization. Well, how much delay is this? If there's a lot of queuing delay, we go minutes. If very, very low, only 1%, we go milliseconds. So minutes, milliseconds, well, that's, say tens milliseconds or hundreds milliseconds, right? So I'm trying to be a bit generous here and use 10 milliseconds only. And so total delay here about 2.01. And 60% of that plus 40% of milliseconds. The dominating component is the 2 seconds. So you see here, the overall total delay on average is going to be about 1.2 something seconds. Is this better than scenario 2? It is, right? Scenario 2, you have at least 2 seconds. So what's amazing about web caching is this. The benefit is not just that it's cheaper, but the delay is also lower. And the traffic coming down this way is also lower. Hey, we did not spend any money here, and we also saved some bandwidth here as compared to scenario 1. So there's more traffic can come down this way. Isn't it nice? And that explains why we need web caching, right? It's to reduce the delay. This is also called the response time, okay? That meant the time it takes to issue the request all the way to the server and bringing down the web object. The round-trip delay of the request and response messages. It also reduces traffic, save a lot of bandwidth on the access link, and it's very cheap. Now, an extra benefit we didn't talk about is because we did not assume the uplink bandwidth of the servers being the bottleneck. If the server is poor, meaning having poor content providers out there, then, let's say that the server here is poor. It cannot afford too high bandwidth uplink. Then reducing the amount of traffic going this way also saves poor content providers some resource, some money. And so web caching there also help the poor content providers to deliver content, right? And this could be a good thing because most of the NGOs, they might also have information to disseminate, but they couldn't provide good uplink bandwidth. And that actually gives rise also P2P file sharing. The idea of P2P file sharing is also, hey, if I have the copy of the content and another peer grab a copy of it, then this other peer can help serving the other peers. So that peer there is working pretty much like a web cache, isn't it? Like a proxy server. So you could actually think of a P2P network, a network of these proxy servers. Okay. And you saw a bit already. Next slide. Coming next is going to be the second application in chapter 2. And we'll look at how FTP defines its application layer protocol.
All right. Next is FTP, but we don't have enough time really to play the FTP video. So we'll actually follow by going through the Q questions. So there's a question from Xuehan about cookies. And those who have questions in mind, but you don't have time to type it up, feel free to do so now. And those who wish to start having lunch early, feel free to go. You can always come back to the video to follow up on the Q&As. And now, okay, we'll just jump to Q&A. Okay, so this is Xuehan's question about cookie. Yeah, so he was asking, I guess Xuehan, you have the spirit of a hacker. Is it possible to modify the cookie number sent to the backend server and log in to someone else's email account or bank account? You know what? It's possible. It's very possible. For example, I don't know how you access your Gmail. What I do is I use Google Chrome and I log in on Google Chrome and then the Gmails will be pulled automatically that way. So that is a little bit risky. So I only do that on home machine that I own, that I'm the only one having access. So if someone else access a machine like that, have access into a machine like that, this someone else get access to my email. Yeah. So that is saying that this is not exactly hard to do. And you can actually potentially try random cookie numbers and see how you do it, how well you do. So nowadays, many of the websites would make sure that the cookies are somewhat random, so that it's not that easy to hack into. So you also want to be careful going to these websites where, hey, if you do not log out explicitly, the next time you visit the website, you see yourself logged in already. You don't have to log in again. I think nowadays many of the shopping websites still do that. So you can remain online. Yeah, bye, Wei Yun. So guys, feel free to go. So shopping websites allow you to stay on for some time. Okay. I'll miss you too, Wei Yun. Can you show us how to do it? Well, I can look it up. Google Chrome's web caches are now binary form. It used to be text and it's very easy. But Google Chrome now's caches are binary form. So unless you log in, it's a little bit hard to see once cache. I can look it up and see if there are certain websites keeping their cookies in a very simplistic way. Okay, so maybe I can show you some, but don't hope too high. So some of these shopping websites, they set cookies too. In fact, many of the sites you see, they pop up and say, hey, whether it's okay to set cookies for all. All right, bye. But you can also select, you set cookies for some that are necessary, but some for performance or for advertise tracking purpose. So shopping websites, a lot of times these days would time out the session. So you could connect back to the shopping website, but after a while, or with just cookies, but after a while, you need to re-log in. So this is to avoid somebody else sniff your cookie for that particular website and try to log in on behalf of you. Or not necessarily logging in, but connect on behalf of you. All right, so I hope that addressed the question. That's potentially doable, but you need to be you need to be able to hack into someone else's system to get the correct cookie ID. And as I said that nowadays many of the websites set the cookies in a more or less random way, so it's a little bit hard to guess. The cookies nowadays are also quite long. Okay, no problem. All right, so bye guys. Oh, okay, so Shihan has yet another question. Is the term cache the same as... Yes, it is. Exactly, Shihan. Okay, Yangxin, bye. It is much like the caching when you're learning computer architecture, right? So inside a computer, we also have a hierarchy of memories. Okay, bye guys. So we have like hard drive, and then we have the memories. We call them RAM, right? Those are more expensive, but much faster than the hard drive. And on top of that, we have the cache. Those are super fast, but we don't have much of these caches. So cache there is to hold very, very frequently used data so that the CPU can get these data quickly. So if you think about it this way, the origin server, Shihan, was like the hard drive. And the local cache was the very high level cache, super fast, but not much space, and keeping the origin data, the data from the origin temporarily for access recently. So the cache is an English term that means the same. Okay, a temporary storage for fast access. I don't know if the brain also works that way. Sometimes I think we also have a section of the brain doing long-term memory and some short-term memory. And so the short-term memory, you can also think of it as a cache, a memory cache, brain memory cache. Okay, very good. Very good association there, Shehan. All right, bye, go. Yeah, storing the cookies is quite storage intensive. So Shehan is having a conversation here with me. Yes, storing cookies is can sometimes be storage intensive, especially if you browse a wide variety of websites. But usually the cookie space for one website is somewhat fixed. There's only a certain amount of things they track. Nowadays, especially in US and Europe, there are rules set up, and the companies need to follow these rules. Only user explicitly saying okay, then otherwise they cannot track too much stuff. But there's no such thing in most of the Asian countries yet. Maybe Japan has this, Korea, but I don't know about Taiwan's rules about setting cookies. So many of the Taiwanese websites, I don't think they are very conscious about asking the users to set the cookie permissions. But if you go to US websites or European websites, hey, you see, do you allow these cookies, or please set your cookie permissions. Okay. But once you set what cookies you allow, the amount of space required for that website is fixed. So the matter is more that how many different websites you go to that require you setting up the cookies. So it would take someone who's very, 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 very diverse to really occupy a good chunk of story on your hard drive. So it takes space, but whether it's intensive, it's really up to the computer. If you have a terabyte there in the hard drive, then it's probably not much. All right. Sorry. So any other questions? Oh, hey, it's already past 12:10, but we do have office hours following the lectures. Yeah, definitely go, Xuehan. Go grab lunch. If you have other questions, feel free to call in. Polly is going to stay on for a little longer to grade the quizzes mainly. All right, so the quiz this week. Right, exactly. Okay, very detailed. It's the rough explanation. Team 4, TCP, since the delay is allowed. Okay, good. RO, PUBG, UDP. Yeah, so Team 4 focus also on the delay requirement when you guys are making choices. Very good. Okay, bye, Wei Xiang. So I was just reading your answer for quiz number 8. Okay. Well done for quiz number 8, Wei Xiang. And then Yo Yu, let's see, Team 14. Have two kind of opinions. Okay. Split opinions within the team. Farmville uses UDP. Since packet loss is not a big problem to this game, yeah, it's more or less casual. PUBG, yeah, TCP, right? Packet loss, not good. And in case there's not much congestion, right? And once you set up a TCP connection, you let it run persistently. The initial delay will be long, but subsequent delay will be short. Very good. So I don't know if you know about having a persistent TCP connection yesterday, but obviously today you learned about persistent connection. Yes, you could have a persistent TCP connection for all the shooting actions. So you can potentially have short delay and no loss. And another member think this. Farmville. Okay, TCP to PRI, but I guess the other member think that Farmville is a little bit serious. And the delay requirement, however, is a little bit more relaxed. Okay. PUBG needs real-time interaction, so UDP better. And human beings can probably do something extra to recover from the air. Okay. Personally, okay, I guess Yo Yu has some personal opinion. I like games like PUBG have reaction like they use UDP, I see. And we think we can mix, okay, I see. So the split opinions are on the first two games, okay? But for the role-playing games like RO, you also think that a mix of TCP, UDP is necessary, right? Very good. Keke here. Farmville TCP, because we could wait for the delay while playing such farming game. Yeah. Oh, hi Catfish. So maybe I should end the stream. So let me admit you in and let me end the stream now. Hi Catfish, just a second, let me end the stream here.